Hey, hi everyone, and welcome to Building AI from Nothing, learning everything from scratch and going against the convention of uh, reinventing the wheel is bad. So, this is the part 4 of the video lecture series. In the first part, we covered semiotics, definition of meaning, origin of number system, we developed statistics, coordinate geometry. So there is a lot of things, the mathematics, but when you're learning AI or mastering AI, you don't need to learn everything related to maths. We are just reinventing those tools and we are using those things. We also talked about algebra, how it deals with variables, placeholders, continuous discrete mathematics. We talked about functions, how it maps one values to another, and we talked about linear transformation, how they preserve the structure, and nonlinear transformations, anti-tuples, vectors. We did a little bit of coding where we basically talked about variables, how to write function and all that. In the part 3, we talked about calculus, which talks about math of change, where we discussed how to calculate derivatives. We wrote code related to that, where we had like n numbers and we calculated derivatives of n minus 1 points. Finding the roots, we talked about Newton-Raphson method. We talked about random numbers, code, and data generation. This part is going to be mainly about data generation. Scaling is one of the important thing. Scaling is also related to, I would say, transformation. So we'll do both thing, and transformation in itself is also mapping. And if you'll dig deeper, or in the future we'll also talk about like how this is neural networks are nothing but transformation of spaces. We'll Next we'll talk about optimization techniques. uh, we'll probably go with Newton-Raphson or gradient descent, and developing general framework of fitting problems. What is model learning and machine learning? Cool. So let's get started with the coding part first. In the last video, we basically wrote a function which was able to generate random numbers. If you give it a count, let's say 5, it was able to give you. So let me just quickly run this ctml tutorials and then node index.js. Cool. So we generated, let's say, 5 random points, and then we used our statistical knowledge to calculate the mean, variance, and standard deviation. And from calculus, whatever we had defined, we calculated the derivative. So we have very basic tools ready to dig deeper. What we'll do today, we'll start with, yeah, data generation we already covered. So let's talk about scaling first. And trust me, scaling is very important. So, and I'll be adding the GitHub link of this repo. So if you want to explore later how we developed the code, you can go ahead and do that. So scaling, what does scaling mean? So let's say you have bunch of numbers like 12, 13, minus 9, 10, 20, 90, 108, 78. Okay, so bunch of numbers are there. Now, I would say you need to map these numbers between, let's say, minus 10 and 10. So what are we doing here? We are basically changing the range. We talked, right, that uh, there's a range which is in what, from what number to what number that thing spans. That is what we call as range. So all of these number need to be mapped between minus 10 to 10. So how would we do that? And before we do that, let's think of a number which lies between, let's say, x min to, and this is your actual number, and this is x max. So this number, which could be any number from this, lies between x minimum and x maximum. So first step, what we can do is we can subtract x min from both sides. So if you'll subtract x min from both sides, this side will become 0 your this number will become x minus x min, and then this number will become x max minus x min. Cool. And now, so I'll tell you the funda. Generally what we do is we leverage in the whole number system whatever we have developed. There's special things about 0 and 1. The special thing about 0 is if you multiply 0 with any number, it still remains 0. Okay. And with 1 is if you multiply it with the number x, it becomes that number. Okay. So 0 and 1 will leverage that property. So we'll try to this is called normalization. So right now this is here. So if I, let's say, subtract or divide this number with this same number, this will become 1 and this will remain the same number. So the range will now become 0 less than this. We'll keep this number as it is and we'll divide by this number. Just this. And the range becomes 1. So here you can say if you have an input of x and you do this operation on that number, the range of the numbers becomes 0 to 1. This is good, right? So if I have to write a function which basically, let's say, takes an array and this number will call normalize. It takes an array and it should return a function in the end which takes the input x and returns the normalized value. Perfect. Now how we'll do that? We'll do const, we'll calculate these values. X min is equal to math dot min of this array, and we'll do const x max is equal to math dot max of this array. By the way, we are skipping some of the edge cases where what if all the numbers are same, so we'll ignore that for now. Okay, now we'll write the same thing what we wrote here. So if x is the input, what we are returning, we're returning x minus x min divided by x max minus x min. Perfect. Comment this. Perfect. So we had, so we'll again take this whatever the code we had. So data is the one which had all the numbers generated. What we'll do is, this is already between 0 and 1, right? Get random number. So we'll just add, let's say, 10 to this. Okay, so our numbers are now between 10 to 11. So we want to normalize those numbers. So our data set is 10 to 11 and we want to normalize that. So what we'll do const normalize is equal to, we are taking normalize and we are passing an array. So this is returning a function. Okay, and what we need to do with that function, we need to pass so that we pass data here. Now data dot map will pass this normalized value, normalizer. So this is a function which does this, and we'll do console.log. Let's run this. What did I miss? Okay, so the minimum value which we had was this, and maximum value was 10.58, this. So it calculated those values and it returned a function which, whenever you feed something the data, it normalizes. So all of these number got mapped to these values. Perfect. So this was a single normalization. We'll also learn there is something called ler. Let me comment this one. Ler, which is also known as linear interpolation. So imagine you have, let me just write it so it becomes very intuitive to you. You have A, B, and T, and it is defined as A plus T into B minus. Now, what is the intuition behind it? It basically talks about if in the number line, let's say in the number line, you have A and B, if you want to find a point T in between, what you'll do, if let's say if T is equal to 0, what will happen? This term will become 0 and you will be here. If T is equal to 1, this thing will become B minus A will cancel out with this and this will become 0. So this T is basically controlling where you are between A to B. Perfect. So we developed this, and by the way, whatever we did here, this is same as this. For example, I can also write the normalization like this, normalization, and this where you have x min, x max, and you want to map it with y min and y max, and then you will feed the actual x value. So this is also become so you're in this lerp, the value which you want is y min and y max. So this will become lerp min comma y max and then t, right? This is the t, and this t is basically your x minus x min divided by x max minus x min. If you'll calculate, this becomes the same thing. T, cool. Now, one thing we should note throughout these, we are doing whatever we are doing, the distance or the relationship between these values. So, structure basically is preserved. What do I mean by structure? It means the order is preserved. It will never happen that if your input value was, let's say, 1, 10, 30, 60, it will never be mapped like 60 will become this side, 10 will become that side, like that. It won't happen. Even though your values are changing, the order will remain preserved. Okay? And whatever we are doing so far, these are all also known as linear transformations. So the b2 minus b1 divided by a2 minus a1 will always remain same. So I can say the gap ratio or slope will remain same. So far what we talked about, we are now able to do a value ranging from x1 to x2. We are able to map it to y1 to y2. It could be bigger, smaller, but we are able to do that while preserving the structure. So this value will be mapped here, this value will be mapped here, like that. It will be always one to one. And if you do this also, then also the structure is being preserved. So this is related to scaling and transformation. Can I say this scaling is also a function or a mapping? Yes. So scaling is also the same thing. Now, uh, what if I write something like this? Const transfer. Okay. So in this transformation, we basically did two things. There are two things that are, if you look deeply, there are two things we are doing with the number. We are scaling them or we are shifting them. What do I mean by that? So let's say const transform. So this is my transformations, and I'm defining things like there is shift. What does shift do basically? It takes the input value, which is C, it takes the input value number, and it basically outputs C plus X or X plus C basically. Okay. Then you have scaling. Scale. In scale, you take a number, let's say M, and you do M. You take X, and then you output basically M into X. By the way, how I am writing this is known as functional programming, or you can say currying basically, where I am just splitting these into multiple arguments. Why we are doing that? Because so that I can have half curried function. You can just read about currying because we will be using a lot of currying. Now if I want to, so what will happen? So const, I can make small functions. So let's say 10 shifter, shift by 10, transform dot shift. So this is a function. Whatever number you will give it, it will always output console dot log shift by 10, and let's say we give it 20. What will happen? I'll get 30. And if I use, instead of shift by 10, I can also write const scale by 10, right? That means multiply by 10. And I'm writing transform dot scale by 10, and we'll use this function. What will be the new output? 200. Got it? So these are small functions we are doing. Here also we did the same thing. Now, and I'll help you be more intuitive, develop a more intuitive way of doing this. So you had a number x1 to x2. What you will do first, you will basically shift the whole number so that x1 goes to origin, right? So this was your x. So you will do something like, so that, so you will shift by minus x1. Got it? So everything becomes like that. So this side it will become 0, x will become x minus x1, and this side will give in x2 minus x1. Then we'll scale everything by 1 by x2 minus x1. So scale by 1 by x2 minus x1. So your whole scale will become now 0 divided by x minus x1 divided by x2 minus x1, and this becomes 1. Perfect. But now our aim is basically to map it to y1 to y2, right? Aim is to map a range of x1 to x2 to y1 to y2. And guys, I understand we're spending too much time in these interpolations, and trust me, if you master these concepts, you will start seeing neural network is nothing but a number crunching machine, which is a combination of these small logical units only. We'll also add nonlinear transformation, which is also another part of it, which talks about shift, scale, and warping. Warping is the higher order nonlinear functions. Not need not be higher order, basically nonlinear functions, which basically maps, doesn't do linear transformation. It could be sigmoid function, it could be hyperbolic tan function, sine function, all of these things. So we are investing time in building these small tools. We developed numbers, we developed things related to statistics, mean, median, variance. We talked about uh, uh, we talked about other mathematical tools. What were there? Coordinate geometry, which we talked about algebra, we talked about calculus, derivatives and all. So all of these things where we are investing time. Similarly, scaling, we are investing time because scaling will help us. Okay, now, so we did shifting, we did scaling. Now, see, these are two things. We need to ensure that both gets adjusted in a way that this number becomes x1, okay, and this become number become not this number becomes y1 and this number becomes y2. So you can think like, what if I add y1 on the both side? But if you'll do that, you'll realize y1 here and y1 here. If you'll try to adjust this number, then this number, so it's like handling two variables at the same time. So what rather we can do, we can scale these numbers with the new range. And what is the new range? The new range is y2 minus y1. So scale by y2 minus y1, and you'll see what will happen. This number will remain 0. This becomes, let's this into y2 minus y1. For now, I'm just writing this as t variable so that it doesn't confuse. And then this will also become y2 minus y1. You see what we'll do now? Very simple. We'll just add y1 on the both sides. So this will cancel out. So we'll again shift by y1. So this will become now y1. The last value will become y2, and this value will become this plus y1. Perfect. So did you see, like, we developed a way of doing interpolation. So if I have to write this same thing with the tools which we have written, so imagine there's a number, yeah. So normalization we wrote like this, right? So I can also write normalization with this rule, right? So it is something where we basically do const, that's const x min is equal to your data dot add dot min of data. We'll also do x max, and this becomes max. And let's define the new range. So const y min, we'll define it as, let's say, 100 minus 100. So we are increasing the scale actually. A const y max we're defining as 100. Perfect. So how the transformation is now looking like? Let's do the same thing. Let's define the interpolation. And by the way, if you'll see here, this again becomes the lerp, what we defined here. So what we can do, we'll write step by step. So first, what we are doing, const new scaled value of x. We want to write a function which gives me new scaled value based on these parameters. So what we did first, we shifted by -1. So let answer is equal to, we'll keep doing on the same number. uh, we did shift, so transform dot shift by how much? Minus x1. So minus x1 is your x min. into got it. Then what we did with this number, we answer. Now this number will become input for the next. So then again we did answer is equal to transform dot scale, transform dot shift this into x, because x is the input. Yeah, now this answer will become input for this. We'll pass in the data like this. And how much are we scaling by? We are scaling by 1 by x2 minus x1. So 1 divided by x max minus x min. Again answer is equal to, we did scaling again, transform dot scale, and we did y2 minus y max minus y min, and then we did shift by y1. Answer again, this will be right here. Answer is equal to transform dot so y1 is your y min, and then feed the answer here, and then return the answer. Perfect. So we can also do console log new scaled value of, let's say, 20. Since our range was 10 to 11, so we'll do 10.5. So 10.5 becomes 12.5. Let's do the same value so that we are sure we are getting the right numbers. So what we did here, did we do lerp anywhere? Oh, we can use this normalization, right? So we'll do normalization. We'll pass in the x min, x max, y max, and then we'll pass in 10.5. Very good. We'll console log the same thing. Perfect. So we got the same number. You can ignore these last few digits. That's related to accuracy, but let's do this. Perfect. So far we developed the tools of scaling. There's one more thing. So throughout these we were marching the numbers in the same scale. We were preserving their structure, but there are other scales also, and there is one important tool also called z score. We'll read about that maybe in the next time. But there is another thing called, let's say, log scale, and as the name suggests, what it does is it does nothing, it takes this and it runs math.log of x. We also can think of sigmoid as a scale. Sigmoid, this is also a function which basically takes the function and it returns plus exp into minus x. So if you look at these graphs, sigmoid, tan h, all of these functions, what they are doing is, look at the images, their input is minus infinity to infinity, but their range is minus 1 to 1. That is what tan hyperbolic function, which is symbol, it is evaluated like this. Similarly, you have sigmoid functions. It takes the input value from minus infinity to infinity and it maps it to 0 to 1. So whatever we did so far, we are doing nothing but mapping. We are mapping one set of numbers to another set of numbers to a different scale. And whenever you map the values from 0 to 1, this is known as normalization. Okay, perfect. Now, when we are doing hyperbole or log or tanh, you will realize the structure doesn't remain uh, linear. What do I mean by that? So, for example, let's do log scale. So, let's say log to the base 10 we are doing. So, we have 10, you have 1, 10,000, 10,000. If you'll do log of these things, log 1 will become 0, log 10 1, this will become 2, this will become 3. Here we're doing log of these values. So if you apply this function to these numbers, now the difference between 3 minus 2 is 1, 2 minus 1 is 1, 1 minus 0. But the difference here between these two numbers is huge. Here also huge. Here also 10 minus 1 is 9. So it changes the structure of the data. And this is known as warping. This is what I was telling about. It is also a transformation, but it is a non-linear transformation. Perfect. Next, we'll talk about Newton-Raphson method. We touched upon it in the last video. Newton-Raphson method basically says if you have a function like this and you have to find the roots. What are roots? This is, let's say, y, and this is x. The points, the value of x where y is equal to 0, those are known as roots. And why in mathematics, why this is important, or in machine learning this is important? Because eventually we'll define some error function and we'll try to find the values for which this error function becomes 0. And we also learned that in the calculus, the tangent gives you an idea that where you should move. So for example, if you are here and your f dash of x is positive, that means, and your f of x is also positive, that means if you are at positive and you want to go to 0, what you need to do, you need to subtract something from there. So you will move in this direction, because if derivative is positive, what does derivative positive means? If you increase x, y will increase. So you need to decrease x to decrease the y. Similarly, if you are here, your y value is actually negative, right? But y dash is still positive. So what you will do, you will still you will move in this direction. So you come up with a formula where x of n plus 1 is equal to, I'll show you note method. अभी मत कीजिए ना. So Newton-Raphson method basically says x of n plus 1 will be equal to x of n minus f of xn divided by f dash of xn. So this is Newton-Raphson method, and this is an optimization technique. Perfect. We did a lot of coding today, and we tried to understand scaling problem. How I'll just summarize. We basically learned scale, shift, and warp. By the way, these three things are the only things which we do in whole machine learning AI world. This is what AI world is composed of. And there are different ways of looking at the same thing. When you look at from the coordinate geometry point of view, you will say that you are transforming the space basically. Uh, Perfect. Now, uh, let's do this first. What is a model, and what do you mean by learning? So think of this like this. Whenever you learn something, so when you were a kid, you were tasked to remember tables. So remembering is also a very crucial part of learning. So uh, you get an input value and you need to give the output which is, so if you have a table of, let's say, 4 5, and if I ask you 4 into 5, you'll say 20. And how did you know that? Because you remembered it. But there's also something where if I ask you what is 4 into 12, even though you didn't remember the table of 12 or 4, you are still able to give me the answer 48. How? Because you understood the concept of what is multiplication. Okay, so remembering the fundamentals, which is basically part of the training, and then using that learning to give me answer on the unpredicted data, that is called learning. That is a simple definition and the core concept, similar to what we do in our day-to-day life. That's what you define learning, right? Now, what is a model then? So learning, we understood. Model is something which basically defines, for this input, this is the output. So the simple definition would be something like, model is simply a mathematical function that approximates to the reality of the value, output value. Okay, so model is nothing but a mapping function. So far we were investing time in learning mapping. There are different types of mapping. Why? Because that's what models are. Models are nothing but functions. If you write a small function like this, that is also a model. This is also a model. This is also a model. All of these things are model only. Not precisely given the items, given the current definition in the AI world, but you can argue with someone saying, yeah, I would say this is also a model, because it is mapping your input space to an output space, and it is giving you the answer. So that is also a model. So how are we saying that? What is machine learning? So machine learning has multiple parts. We have supervised learning, unsupervised learning, and we also have reinforcement learning. There's another field, I forgot the name. I think generative AI or something. So we'll focus on supervised learning, by the way. So whenever you give a model, not a model, whenever you give machine a set of data points, an observation, and the machine is able to come up with a hypothesis or a model which basically predicts the output for given data as well as unseen data, that then we say the machine has actually learned. It has learned from the data because it is able to predict those values. Okay, so here we'll say machine learning is finding the function which mimics the real output based on given input. Good. Now, how do we do that? We define something called as hypothesis. Hypothesis is nothing but a function or an untrained. uh, It is also function, a model. You can say that. So hypothesis is something. Let's say you are given a set of data points like this. What you can say? You can say it. You can come up with a hypothesis saying that this is something which follows a linear order. So hypothesis is saying for a given input, I can find a straight line equation y is equal to mx plus c, which basically predicts these outputs. That is known as hypothesis. So you have a hypothesis, then you define a error function, because you will define this hypothesis with some parameters. So your function is function of parameters. You define an array function, and then we will use the calculus to optimize these things. This is how generally, and then this will happen in the loop so that we find a, we will tune the function, we will basically tune the model, tune the model parameters to minimize the error. And whatever parameters we get, we call those as uh, we call those as model parameters or trained weights, not parameters, trained weights, I would say. Perfect. I think this again got stretched out too much. We spent too much time on the scaling, but scaling is important, as I said. And next video I will write some code. So if you have time, please go and read about canvases. There's a component in HTML called canvases. We'll use this. We'll basically use this canvas field, HTML element, to plot the data points. And then in the next video, we will cover up. We'll basically go ahead and do the linear regression. We'll complete that in the next video with the plotting and everything. And yeah, then your actual machine learning, that is like linear regression is basically a hello world of machine learning. So we'll do that in the next video. Cool. Thank you so much.